Hello, sir. Welcome to my presentation on experiment for uniform condensation and conformal validation, also known as PCM. In this experiment, I will demonstrate how a continuous sinusoidal signal is converted into digital form. The main objectives are: one, normalize sinusoidal signal, apply uniform contribution using different representation, generate quantizer indices and PCMs, measure quantization error and screener. Compare the measured result with students. The experiment also induces waveform plots and error analysis, loading factor analysis, and a comparison between mid-rise and mid-fixed voltages. Now, here you can see the theory recap. Uh, Uniform container divides the input in range into equal spaced levels. The number of the quantization level is n is equal to n, where n is the number of bits. The quantization step size is delta is equal to is max weight. For the mid-rise quantizer, the input signal is converted into an index using the floor operation. The index is then flipped between 0 and n minus 1. The quantized output is reconstructed from the center and center of each quantization interval. The theoretical SQNR for full sinusoid is SQNR in this way 6.028 plus 1.6. The equation predicts that every additional bit improves the SQNR by approximately 6 decibels. Here you can see in this step, I put numpy for numerical calculation, pandas for organizing a result, and matplotlib for plotting. I also set the random speed and configure the appearance of the graphs. The different colors are assigned to the original signal, content signal, and error signal, and the theoretical results. So, in this cell, the cell defines a main quantization function. The function takes the input signal, number of bits, maximum signal amplitude, and quantizer time. First, it calculates the number of levels and the step size. Then it performs the following operations: shifts the input signal, divides it by the quantization step, applies the floor operation, clears the result to the valid index range, looks up the reconstruction level, converts every index into a binary PCM. The function also detects overload when the input exceeds the allowed range. So in the in this cell, the function decodes the PCM word back into quantizer indices and reconstructed signal levels. The bitstream function here we can see the bitstream function combines all PCM words into one continuous sequence of bits. The matrix function calculates quantization error, mean squared error, signal power, SQNR, maximum absolute error, error variance. The final function calculates the theoretical SQNR for comparison with the measured result. Now, here we can see the signal normalizations. In this cell, I generate a 1 kilohertz sinusoidal signal. The sampling frequency is 44.1 kilohertz and the signal contains 44,100 samples, representing 1 second of audio. The original amplitude is 3.7. I first remove the DC component and then normalize the signal to the range from -1 to +1. The output confirms the signal range, mean value, and signal power. The normalized sinusoid has signal power close to theoretical value, a square by 2 is equal to 0.5. Here's the very close to the theoretical value. Now, here we can see the mandatory validations. The cell verifies the encoder is working correctly. The first check confirms that all indices are between 0 to L minus 1. The second check confirms that every PCM word has exactly n bits. The remaining checks verify that every code word contains only binary digits. Encoding and decoding produces the same quantized signal. The granular error is no greater than delta by 2. The total bitstream length is equal to n small n into capital N. Here you can see. Here only. Here you can see this. Everything is passed here. You can see. So now, in this cell, I quantize the signal using all selected bit resolutions. For each resolution, I calculate the quantized output, error, MSE, maximum error, measure SQNR, theoretical SQNR, and bit rate. The mandatory validation result should show that all required checks have passed. So here you can see every required check has passed, have passed already. This cell demonstrates that increasing the number of bits improves the quality of the reconstructed signal. So after that, here all the mandatory variables all are passed here, and here we can see the SQNR improvement. This cell calculates the change in SQNR. Okay, SQNR between consecutive bit resolution. The measured improvement should be close to 6 decibels for every additional bit. The mean measured improvement is approximately 6.15 decibels per bit, which agrees well with the theoretical prediction of 6.02 decibel per bit. Now, here I display the complete code of 3-bit quantizer. Since A is equal to 2 to the 3 plus 8, there are 8 quantization levels and 8 possible binary words. The table shows the index. Here, the table shows the index, binary PCM word, decision interval, and reconstruction level. This makes the operation of the quantizer easier to understand. The section displays the first 12 input samples. Every sample we can see, every sample we can C. Original value, quantization error, quantizer index. The PCM words are then joined to create one continuous bit stream. For a 3-bit signal sample at 44.1 kilohertz, the bit rate is RV is equal to NFS equals to 3 into 44.1 is 132.3 kilobits per second. Here you can see 132 kbps. The receiver successfully decodes the bit stream and reconstructs the quantized signal. Here, the quantized. Here we can see. Now, this is the first visualization. The blue curve. Here, the blue curve represents the original sinusoidal signal, while the orange staircase represents the quantized signal. With 2 bits, the staircase is very coarse because there are only 4 levels. As the resolution increases to 3, 4, and 6 bits, the quantized signal follows the original waveform more accurately. This clearly shows how increasing the bit resolution reduces quantization error. And cell 13, this plot shows the transfer characteristics of the quantizer. The horizontal sections represent levels. For higher bit resolution, the number of the steps increases and the step width becomes smaller. The shaded regions outside -1, 1 show the overload region. Signal entering the region are clipped. Yes, entering these regions are clipped. The second graph shows the quantization error within the normal range. The error is limited approximately to minus delta by 2 to delta by 2. Now this slide displays the quantization error for 3-bit and 6-bit quantization. The dotted line. The dotted lines shows the theoretical error limit of plus minus delta by 2. The error is much larger for 3-bit quantization because the step size is larger. For 6-bit quantization, the error is significantly smaller. The histogram shows the distribution of error. At high resolution, the distribution becomes closer to the ideal uniform distribution. This graph compares measured SKNR with the theoretical equation 6.02n plus 1.7. The measured SKNR increases almost linearly as the number of the bits increases. The second graph shows difference between measured and theoretical SKNR. The measured result is slightly below theory, especially at low resolutions, but the difference becomes smaller as the number of bits increases. In this cell, I vary the amplitude of the input signal. The quantizer step size is determined by Xmax and does not change when the signal amplitude is reduced and does not change when the signal amplitude is reduced. Therefore, a smaller signal uses fewer quantization level and has lower SQNR. When the amplitude is reduced by half, the SQNR decreases by approximately 6 decibels. When the amplitude becomes greater than Xmax, flipping occurs. Here you can see that the scalar then decreases rapidly because of overload distortion. Overload distortion. Here you can see the value. This cell compares mid-range and mid-range quantization. The mid-range quantizer has no reconstruction level exactly at 0. The mid-range quantizer includes a reconstruction level at 0, which is useful when representing silence or very small signals. The printed result shows the HQNR for both quantizer at different resolutions. The difference is generally small, but two quantizer structures do not produce identical results. This section examines whether the quantization error behaves like white noise. For white noise, the autocorrelation should have a strong peak only at 0 lag, and the spectrum should have a relatively flat noise floor. At low resolution, the error shows clear structure in the autocorrelation and harmonic peaks in the spectrum. This indicates this indicates that the error is not completely random. It contains deterministic distortion related to the unnecessary input. At higher resolution, the error becomes more noise-like. Here you can see. For whiteness, the autocorrelation should have a strong peak, only at 0. Here you can see that. The first test checks whether the clip fit sample is responsible for the QNR difference. The result shows that removing the clip sample does not significantly change the result. The second test divides the signal into amplitude regions. The largest excess error occurs near the positively and the negative peaks of the sinusoid. The third test uses a uniformly distributed random input instead of a sinusoid for this input. The major error variance agrees with delta square by 12. There you can see that. This confirms that the quantizer implementation and the theoretical model are correct. The difference occurs because a sinusoid does not have a uniform amplitude distribution. The final series summarizes the experiment. The measured results confirm that SQL increases by approximately 6 decibel per bit. MAC decreases by approximately a factor of 4 per bit. The maximum granular error is approximately delta by 2. The uniform noise model becomes more accurate at higher resolutions, reducing the signal amplitude reduces scalar. Increasing the amplitude beyond full scale causes severe cleaning distortions. Here you can see that the measure examiner is slightly lower than 6.02 n plus 1.76 decibel because the sinusoid has a an arc sine amplitude distribution. It depends more time near its peak. It spends more time near its peak where the quantization error is not perfectly uniform. Therefore, the theoretical SQNR formula is an approximation that becomes increasingly accurate as the number of bits increases. Here you can see that. It's increasing. So, to conclude, the experiment demonstrated the complete process of uniform quantization and PCM encoding. The signal is sampled, normalized, quantized, converted into binary words, transmitted as a bitstream and decoded. The main result is that every extra bit approximately doubles the number of quantization levels, reduces the quantization step and improves the SQNR by about 6 decibel. This experiment also shows that the effects of signal loading, overload distortion, quantizer type, and signal dependent quantization error. Thank you, sir, for watching my presentation.